So in this particular lecture video, we would try to understand, we would see actually the exact application of the complement representations. The application being the arithmetic operations of addition and subtraction that we can do in the complement representation. So previously in the normal representation of a number system, in a general number system, like we have seen in binary, octal, hexadecimal, we could do addition. We could even do subtraction when of two numbers a and b when b is less than a. But if we could not do the other way, that is b minus a, we could not do. So we could not do an operation where the result would come out to be negative, because there was no way to represent a negative quantity in the normal number systems. But when we come to the complement representations, then we find a way to represent the negative quantities, and now we are able to deal with the negative quantities and perform the arithmetic operations in the normal way as you do the operations in the normal number system. So let us go ahead and see the exact algorithm. So we would cover in this lecture the binary number system. So we would be looking into the twos complement representation and the ones complement representation, and how we are going to subtract two numbers in twos complement and ones complement representation. So we are concerned with subtraction because that is the operation that we are not able to do completely using the normal method of subtraction. However, we must remember that we can also do the addition operation of two numbers in twos complement representation. That means we can also do a plus b. Actually, what we are doing while subtracting a number, so when we are doing the a minus b operation, we are actually doing a plus of minus b, and minus b is represented in the twos complement representation. So what we are doing, we are actually adding two numbers which are in the twos complement representation. One number being the twos complement representation of a, and another number being the twos complement representation of minus b. So in this example we are showing you the example where a and b are both positive quantities, and we are doing a operation a minus b and b minus a. But please be aware that a and b can be positive or negative and or whatever. Okay, it doesn't matter. What we are actually doing is we are writing them down. So if we have a minus a minus b, suppose, then we are actually writing down the twos complement representation of both minus a and minus b, and then adding them together. That is what we will do that time. So here we are showing you a minus b because that will reveal two things. One is the twos complement representation of a positive number. Second is the twos complement representation of a negative number. And then the simple addition algorithm we will perform on the twos complement representations, and we would learn to interpret the result that will come out because of this arithmetic addition. So the interpretation of the result will also be important. As you can see that in the first case the result will be greater than 0, whereas in the second case the result will be less than 0. So both will have a different interpretation. So that we will also learn by the help of these two examples. As you can see that your as you can see that you have your numbers. One number is 95. One number is having the quantity value of 95, and we are using 8-bit binary. So the 2's complement representation is in 8-bit. We have to do that. Why? Because the number the quantity 95 can be represented using 7 bits. The magnitude can be represented using 7 bits. So we must have an 8th bit in order to represent the sign. So it could be more than 8 also, but we are limiting it to 8. So the 8th bit, which is the sign bit here. So since we are trying to represent positive quantities in 2's complement representation, we know that they are simply the signed magnitude representation only. So the MSB would be 0 and the other bits would comprise the magnitude. So if you evaluate this part, you will find that this is 95. I leave it for you as an exercise. Similarly, if you evaluate this part, you will see that this is 57. So these are the signed magnitude representation of 95 and 57, which is also the 2's complement representation of these two quantities, since these are positive quantities. However, my operation is a minus b, so I must subtract 57 from 95. So what I need the 2's complement representation of 95 and minus 57. 95 2's complement representation is already seen from here. So Na2c is the same thing as the sign magnitude representation, but what would be n of minus b? So we need minus 57, so minus b 2's complement. So 2's complement representation of minus b would be the 2's complement of this number, 2's complement of this number, which is the number which is the 2's complement representation of plus 57. So the 2's complement representation of minus 57 is the 2's complement of the number which is the 2's complement representation of plus 57. So these terminologies I have been using very accurately, and I also stressed on this in the last video, so you should be clear in understanding, and this also leads us in the evaluation of the 2's complement representation of minus 57. So what we have to do, we have to simply find out the 2's complement representation of plus 57, which we have already found out in 8-bit binary. So we are dealing in 8-bit binary, that is important to note. Then what we do, we take a 2's complement of this and you will get this particular number. You will get this particular number with the 2's complement. So let me use the pen. So when you take a 2's complement, you will get this particular number. Now we do the addition. So you will see that if you do the addition of these two numbers, what effectively you are doing, you are doing the a minus b operation. So the sum or the result is also in 2's complement representation. So please mind it, the result that you will find out is not a binary, but it is in 2's complement representation. And what is the length of the word we are dealing with? We are dealing with 8-bit word, 8-bit 2's complement representation. So the result must also be interpreted in 8-bit 2's complement representation. Now if you do the addition, you will see that you keep on adding this, you will see that this thing comes out, So this is simple arithmetic addition. I hope by now you are familiar with doing this. So you will get this number coming out. Now note that in this number the red marked one is the ninth digit coming up. So an additional bit is coming, and this additional bit is termed as the overflow bit. This ninth bit, so if you are working in n bit complement representations and during some operation, so you are working in n bit complement representation, and during some operation, this operation can be anything. In this case it is addition. So during any operation you find that a ninth bit comes up. So this ninth bit would be treated as the overflow bit or the overflow digit if you are speaking in general. So this is the overflow bit, and we have to have a way to handle this overflow bit. What is the rest of the word? Look at the rest of the word. So this overflow bit is basically the handling in 2's complement representation is that you discard the overflow bit. So this overflow bit is discarded in 2's complement representation or in radix complement representation in general. In radix complement representation, an overflow is discarded. So you discard the overflow and then you look at the rest of the word, rest of the number coming out. So in this rest of the number, you remember that this is in 2's complement representation. So by looking at the MSB, you would be able to understand whether this is a positive quantity or a negative quantity. Of course, this should have resulted in a positive quantity, and you see the MSB is 0, so it is a positive quantity. Now pay attention that if you had not discarded the overflow, then your MSB would be 1 and you would be led to believe that this is a negative quantity, which would be wrong. So you must discard the overflow in this case, and then you look at the remaining number. So in the remaining number we can see that the MSB is 0, that means it is a positive quantity, and now you go ahead in evaluating the magnitude of that positive quantity, and that is it. You get the result. What is the magnitude of that positive quantity? If you can evaluate, and you will get that that answer would be 38. So if you evaluate the remaining part, that is this part, if you evaluate, then you would see that it comes out to be 38. This gives you the sign, so the plus is coming from here, and this is basically ignored or discarded. So your result is plus 38 and you get the right answer. So in the result, if you are asked to find out the result in the 2's complement representation, the number that you will write is this. Discarding the overflow, whatever is there, that is your result. You should discard the overflow and then write the result. You should not keep the overflow in the result. So please pay attention here. So if you are asked to find out the result in 2's complement representation and not asked for evaluation of it, so the result you should write would be this. You should discard the overflow and then write the result, and after that only actually the evaluation starts. Evaluation of the quantity starts after you obtain the 2's complement representation of the result. So this is about A minus B, where we had a positive result. Now look at the other look at the look at it in the opposite manner, like we are doing the b minus a operation, and you know that the result should be minus 38. Result should be minus 38, so the result is negative quantity. Let us see how the 2's complement representation is able to bring out this result. So that would be a complete check that the algorithm is working. Whatever algorithm we are describing here is working. So again, so here b is positive, so we don't need to change b. So the 2's complement representation of b, as you can see, it remains the same. So it remains this, but the 2's we have to find out the 2's complement representation of minus 95. So then we have to actually perform the 2's complement on this particular number, which is the, so this number is the 2's complement representation of plus 95. So when you do a 2's complement on it, you are getting the 2's complement representation of minus 95, and then you do the simple arithmetic addition on these two numbers, on the 2's complement representation of minus a and plus b. So when you do the addition, then you would find that this is the number that is resulting. This is the number that is resulting. Remembering that this number is in 2's complement representation, we have, and 8-bit 2's complement representation, we have to interpret this number. So you see whether you have exceeded the limit of 8 bits. You have not exceeded the limit of 8 bits. That means the MSB now, as you can see, would give you the sign of the quantity represented by this number, and the sign is minus, negative, which is what we should have obtained. However, how to find out the positive quantity? So actual magnitude, how to find out that? We know that this quantity, so this quantity that we have obtained, being the 2's complement representation of a negative quantity, if we do a 2's complement of this number, we will get the 2's complement representation of the corresponding positive quantity, and from that we would be able to extract the magnitude of this number. Magnitudes are same, right? Only the sign is different. So we do a 2's complement. So when we do the 2's complement, what do we find? So this is the interpretation as I told. So when I do the 2's complement, what I would get? I would get this, and the evaluation shows me that the number is, that the quantity is 37. So the result is minus 37, but the result should have been minus 38. So where did we do the mistake? And this is a very common mistake. That's why I wanted to show you this. We forgot to add the 1 while doing the 2's complement. So we must not forget adding the 1 after flipping the bits, or after taking the complement of each digit. We must add the 1 in order to get the number in the 2's complement representation or the radix complement representation. So this addition of 1 is very important. One should not forget this. So please highlight this in your mind, and always remember that one must not forget adding of the 1. Otherwise your result would be wrong. So this is all about the operation in 2's complement representation. As I have shown here, a minus b and b minus a. So in the same way, actually you can also try to see what would be uh, what would be other numbers you can take, other quantities you can take, and try to do the operation and see for yourself that this algorithm really works. However, one big caution is this, that you have noted and you have acknowledged that the result that you obtain, the result number that you are obtain, this ns, that is in 2's complement representation of some n bit. So here 8 bit. So you are restricted in choosing your numbers or the quantities to begin with. You are restricted in choosing the quantities to begin with. That is one thing, of course, because you cannot choose any quantity whose magnitude cannot be whose magnitude representation exceeds 7 bits. You cannot do that. You have to limit the magnitude within 7 bits. That is one thing. So we know that the magnitude would be limited by 2n minus 1. The magnitude, only the magnitude part, 0 to 2n minus 1. This is, we know. This is about your a and b. That is true. But this is also about your s. Please note this. This is something we often forget and land ourselves in trouble. We choose some a and b which would give us an s which is outside this limit. Don't do that. You have to choose an a and b so that your s is coming, the magnitude of s is coming within this range. Only then you will be able to use this algorithm in its proper manner. So I also put forward another caution. Please don't look at any web references for this part of your course. Whatever is there in the web, they may be correct to certain degree in certain situations, but whatever I have seen, I have explored a lot in the web about 2's complement representation and operations in there. They are actually very confusing, and then they don't reveal the complete picture. Don't go into the web for any reference on operations in 2's complement representation. Even many books are not very clear about it. They are only providing results which are valid, of course, but in a restricted setting. But the thing that I am showing you is valid in all settings. Only thing you have to remember, that you should not choose an A and B that gives you a result outside the range of quantities that the number that the 2's complement representation is able to represent. Don't choose initial quantities or numbers a and b which gives you a result which is outside the range of quantities that the system you are using, the complement representation system you are using, with the length of bits, with the number of bits, is able to represent. You should not exceed that range. So this is a very important caution, and if you are not paying attention to this, you will choose your a and b in random, and then you will land into trouble. You will see that the algorithm is not working, the answer is not coming as it should, as you expect it to come. It would not give results if the result exceeds this range. So please be very careful. I have already spent 5 minutes talking about this, so you understand the gravity of the situation. this is how actually we perform the subtraction operation when we can represent the subtraction operation as an addition operation like this. So if we have to subtract b from a, then suppose there is a adder block. So this adder block can be some adder circuit. These circuits we would learn in subsequent parts of the course. So you can have a block diagrammatic representation for the time being. So this we can have only an adder. We don't need a subtractor if we are dealing with complement representations, because the adder can add the 2's complement of b of the number to be subtracted. It can add the 2's complement of the number to be subtracted, and resultant what we are actually getting here is the 2's complement representation of a minus b. Then we have to simply do the interpretation of this 2's complement representation number. That interpretation can be dealt with another circuit, or the receiver can interpret it in its own term. But what we are gaining, we don't have to design a subtractor circuit separately. The same adder circuit can handle both addition and subtraction. This 2's complement representation is basically a 1's complement plus a 1. So you would ask me, sir, okay, how to do the 2's complement in a circuit? So the 2's complement is basically a 1's complement added with a 1, and 1's complement is nothing but flipping the bits. So if you have any binary number like this, the 1's complement is simply flipping the bits, and this flipping of the bits can be done very easily. When you learn about the digital electronic circuits, gates, etc., you will learn that it is a very simple operation, and that can be done very easily. So making the 2's complement is not at all a problem, and that is the way that the arithmetic logic unit actually works. It has the adder, it does not have the subtractor, and this is the way it performs the subtraction operations. Now let us see the operation in 1's complement representation. So we can do the operation also in 1's complement representation, and the same numbers we have taken. So let us go ahead. This is actually the algorithm. The algorithm remains the same. That means we are using the 1's complement representation of the numbers that we need, then adding them up. However, we have to remember two key differences are there. The first key difference is that when we are taking the complement of the number, since we are doing 1's complement, we are not adding the 1, we are only complementing the digits. In binary, we are only flipping the bits. The other the other key difference is this sorry, that we need to add the overflow back to the result. So this is the other important thing. So we need to add the overflow back to the result. So the overflow that we were discarding in 1's complement, in 2's complement operation, that overflow we need to add back to the result if there is an overflow. If there is an overflow. So if there is no overflow, there is no adding it, of course. If there is an overflow, we have to add it back to the result. So this is the two differences, and let me show you the operation. So let us look at what were our 95 and 57. Okay, it's already given here, I think. Yeah. So if I have to do the do a minus b, that means I would like to have not in 2c, sorry, so it should be in 1c, and this is the same because it is a positive number. 1 n of minus b in 1c, it is simply flipping of the bits 1 1 0 0 0 1 1 0. Now you add, so your result in s in 1c would be 1 0 1 0 0 1 0 0 1. I hope I am correct. And here you can see this is the additional 9th bit. What you have to do with the overflow? This is the overflow. What you have to do with the overflow? You have to bring it back and add it to the result. Then what you get? You get this. Now you interpret this the result. So this is actually your final NS1C. This is your NS1C. Okay. So you do the addition and then you see what your NS1C is. So after doing the addition, if there is no overflow, then that is your result. If there is an overflow, you add it back and that gives you the ones complement representation of the result. Now you look at this result and you see that the MSB is 0, that means the quantity is positive, and then you evaluate the remaining parts, which gives you the magnitude. So if you evaluate this, you would see it would come out to be 38. I hope this sort of evaluation is now you are now very comfortable in doing that. Now here sorry, so in what we need to do b minus a, so we need n minus a 1c, and that would be this, simply flipping the bits, and n b1c, that would be remaining the same. Now you do the addition. So after doing the addition, you'd see whether there is an overflow or not, and then you decide whether that is the complement representation. Here there will be no overflow. 1 0 0 1 1 0 1 1. So this is your NS1C, and you have no overflow. This is in 8-bit, and so you look at the MSB and you decide that this is a negative quantity because MSB is 1. So to know what would be the magnitude of the negative quantity, you have to do a ones complement on this number in order to get the ones complement representation of the positive quantity. 0 0 1 0 0 1 1 0, and this would give you the magnitude, which is the same 38. So it is minus 38. So I hope it is clear now to you what is the algorithm. You simply, whichever number you have to subtract, you simply take the complement of that number, of the corresponding positive number to get the complement representation of the negative number. Then you add the complement representations. Whatever result you get, you first look at it a bit, whether there is overflow or not. If there is overflow, what to do with it. If you are in 2's complement representation, you are discarding the overflow. If you are in 1's complement representation, you are adding the overflow back to the result, and that gives you the final result in the corresponding complement representation system. If you are in 2's complement representation system, it gives you the answer in 2's complement representation system. If you are in 1's complement representation system, it gives you the answer in 1's complement representation system. And now you have to evaluate the quantity hidden in that representation. So if your answer has come out to be positive, by looking at the MSB, you can infer whether it is a positive quantity or a negative quantity. If it is a positive quantity, then it is quite straightforward. The remaining bits are giving you the magnitude. However, if it is a negative quantity, then you have to do a complement. You have to take a complement of that number. If you are working in the 2's complement representation, then you have to take the 2's complement. If you are working in the 1's complement representation, you have to take the 1's complement. So after taking the complement, what you will get a positive quantity, because you are taking a complement from a negative number. You will get a positive number, and then you evaluate the magnitude. That would be the magnitude of the same negative quantity, and that would give you the result. So I hope this is clear. You can try to work out with other numbers. You change your A and B, keeping this in mind that your result must lie within the range that your number is able to represent. You have a constricted range because of your choice of the length of the number. So you must not choose your A and B numbers that gives you a result which is outside that range. Please keep it in mind when you are choosing your A and B. Please keep that in mind. So this is all in this particular lecture video. I hope you have understood the algorithm, and if there is any doubt, you can ask me during the live session. So with that, I would conclude, and I sincerely request you at least do this example. Of course, you should do this example in pen and paper, as well as you alter the examples a bit here and there and try to do on pen and paper. So I would also ask you to do one thing. Just for checking how the algorithm actually fails, you can actually take some A and B so that the result is outside the range of our operation, and see what is actually happening, and you will see that the algorithm is failing, uh, uh, and you realize that why this caution that I am so much stressing is so important to uh, maintain. So that is left as an exercise for yourself. You can do that and verify it for yourself that the algorithm will fail. So with that, I would end this lecture. Thank you for your attention. See you again in the next lecture.